Assalamu alaikum, everyone. I hope everyone is doing well. First, can everybody see my screen? If anybody cannot, please let us know in the chat box. Okay, thank you. Okay, great. So let's get started. We have another very interesting read, a paper written by Facebook engineers about how they scaled Memcache at Facebook to serve a very large number of user requests. Over 1 billion requests per second. So this is a very large system, and the paper talks about experiences of designing such a system. So the reason why we are reading this paper is that, as I mentioned, it provides some invaluable experiences of building a distributed system at such a large scale. For instance, at the scale of Facebook, where we're talking about more than 1 billion users and a large number of user requests coming every second. And you need a system that can handle such large number of requests. So this paper provides very interesting experiences, but it's not a paper that presents any novel ideas or techniques. So it's really presenting experiences. And in that sense, it's similar to Dynamo, where it synthesized many existing ideas, but wasn't really a paper that talked about any new idea or scheme. And there are 3 ways that we can read this paper. One is that it's surely a very impressive story of how they were able to build a system with huge capacity and from mostly off-the-shelf software. So those of you who have read the paper would know that they talked about how they used the Memcache implementation for a single server and then scaled it to a large number of servers. So they started off with off-the-shelf software and have been able to build a system that was able to have such large capacity. That's really impressive. However, it's also a cautionary tale of how they did not take consistency, or they did not give consistency that much importance at the start of the design. And as a result, they ran into several issues about how to maintain cache and database consistency. And there were many race conditions that were possible, and they had to come up with fixes for avoiding such problems. And one way to view this is because, consistency, it seems that wasn't a first-class consideration from the start of the design. As a result, they ran into such issues. Thirdly, the paper can be viewed as the struggle between performance and consistency, which has been a central theme in distributed systems. So we have seen this, that as captured by the CAP theorem, there is this tussle between availability, performance, and consistency. And we saw how Dynamo sacrificed consistency. And we'll see now that in the case of Memcache at Facebook, again, they have to sacrifice consistency, allow stale reads to be able to provide very high performance. So this is, again, a central theme, and that we see in different distributed designs. And while the design choices they've made in several places, you can argue, why did they make this design choice? What if they could have made a different design choice? And we would see that there are alternate designs that were possible. But what is really impressive is that the fact that they were able to build a system that was able to handle, such large number of requests, over 1 billion requests per second. So that is something that's really impressive. Okay, so the problem that Facebook had was that they were trying to build a system that would be able to handle a very large number of requests. So over 1 billion requests per second. So this is the scale at which we are trying to design the system. And at the same time, what they want to do is that they want to serve requests with low latency. So they want users to experience low delay. So when user are loading Facebook pages, they want that those Facebook pages should load very fast. And that means that behind the scenes, when those requests are sent to their data centers, the request should be processed really fast. And then the challenge for them is that they have to aggregate content on the fly from multiple sources. So they talk about this in the paper, that on average, 521 distinct data items were fetched for loading popular pages. So when they were showing a popular page, the process of loading that page required them to fetch on average more than 500 distinct data items. So which means that these data items, if they're dispersed on different servers, they need to aggregate them, and only then the page can be rendered. So this requires a lot of aggregation of data items. And if we look at the 95th percentile, they mentioned that 1,740 data items were being fetched for loading a page. So this is a huge number of data items that need to be fetched for loading a single page. Okay. And they also mentioned that they have some very popular shared content that is accessed by a large number of users. And their workload is such that the number of reads are significantly larger than the number of writes. So they say that users consume an order of magnitude more content than they create. And this has a huge implication on the design choices they make, because this means that this is a system. They need to design a system that will have read-heavy workload. If we go back to Dynamo, the implicit assumption was that the number of reads and writes are roughly the same. Okay. Whereas in this case, the assumption is that the number of reads are at least an order of magnitude more than the number of writes. And whenever we are looking at designing a system, this is a very important question to ask. What is the workload? And whether the workload is such that it's read heavy, or whether the number of reads and writes are equal, roughly equal. In this case, it's a read heavy workload. And that's the reason why they opted for a caching system. And so that they could end up speeding up the reads, while the writes, as we'll see, will not be as fast as reads. They also mention that they're okay with exposing slightly stale data to users for a short time. So this means that they are not looking at strong consistency guarantees from the system that they want to design. They're okay if users are shown slightly stale data. Obviously, it's bad if users are shown stale data for a long time, and that's something that they also try to avoid. But they're okay with some stale data being shown for a short time. They mentioned that traditional systems like MySQL databases are slow, and they found them to be difficult to scale. And that is the reason why they went in the direction of using Memcache. So their solution, Memcache, is essentially a distributed key value store. It's a distributed hash table. So it's a distributed in-memory hash table. Servers store a hash table in RAM. Key value pairs are stored in RAM. It's simple and fast. The interface that's provided is you have these put, get, and delete commands. Put to make writes, get to read, and then to delete items, you have the delete command. So this is the interface that they have, and the system that they have is a distributed in-memory hash table. So why they went with Memcache? What was the reason? We could see that Memcache as a in-memory hash table would provide them fast access versus, for instance, going to a database that's storing data in persistent storage. And since they have such large number of requests per second, that would mean that there will be delays occurred in reading and writing requests, and it would be difficult to scale the database, because we know that reading and writing data on persistent storage is significantly slower than reading and writing data in RAM. So that makes sense. That's one of the reasons why they went for using an in-memory hash table. The other reason is that the way their workloads are structured is as follows. So what they have is a workload pattern where they have a large fan out of data request and multiple rounds of data fetching for loading a page. So this is a very interesting graph. This is not from the original paper but from another talk by the Facebook folks, where this graph shows the data dependency DAG uh, for a small request for loading a page. And what it shows is that you have a large number of data items that can be fetched in parallel. And this is what they mean by high fan out. So you have a large number of data items that do not have dependencies, but then you also have some amount of dependencies. So this is showing data items that are being fetched in a serial fashion and have data dependency. And this means that there has to be multiple rounds of fetching of data. So the workload is such that when you're loading a page, you may have many data items and you may have a high fan out, which means that you have data items, many data items that can be fetched in parallel. And then you also have some data dependencies such that some other data items have to be fetched before fetching prior data items. This fan out has important consequences because this fan out means that they can achieve, they can target a certain amount of parallel processing. And so that is one of the reasons why we'll see that how they will design the distributed hash table such that they would want that they can do parallel processing of fetching different data items when data items do not have dependencies. And they would want to fetch these different data items and fetch them fast. Remember, one of the problems is that you have to aggregate a large amount of content on the fly. And if you have data in memory and you can do parallel processing, then you have the potential of speeding up the overall response time or the time to load the page by aggregating the data quickly. So this is really the larger motivation for using Memcache given the workload. The service and storage architecture that they have is as follows. We have seen this tiered architecture, something similar being used by Dynamo. And this is generally the case for any reasonable size web service, that they have a tiered service and storage architecture. And in this case, in the case of Facebook, what happens is that if you have the end user who's trying to load the Facebook web page, its request, when it gets directed to the Facebook data centers, it will be first going through a load balancer, which assigns a web server. And that web server is responsible for aggregating data, for assembling data. But this web server is largely stateless in that it doesn't really store any data. Data is stored in these two layers. So we have the Memcache layer where the data is stored in memory. And this is what we are going to focus on. This is what the paper is about, how they've designed this caching layer where the data is cached. But then they have this layer in which the data is stored in persistent storage. And so they have these two layers, storage layers, and they have decoupled these two storage layers such that they have a separate caching layer where the data is stored in memory. And then you have the database layer where the data is stored in persistent storage. And you would have seen in the paper that they talk about the fact that generally they want that data from the database should be considered as the authoritative copy of the data, because you can have copies of the data in the cache, but when it comes to relying on what is the updated copy of the data, it's always going to be the data in the database. So this is how these services are architectured. Now, when we look at the overall architecture, they have multiple data centers. And the way that they have structured these data centers is that they're saying that they have a data center which is going to be referred to as the master. And then the other data centers are replica data centers or backup data centers. And the master data center is to whom all the rights go. So it keeps the master copy of the database. And all rights need to be sent to this master copy. So this is a geographically distributed storage and service system. You have your data centers geographically distributed. And the way they have architected this is that one of these data centers is going to be considered as the primary or the master, and others are going to be considered backups and replicas. And they're actually going to be storing entire copies of the data. So the master data, the entire data is actually replicated in these backups. If we were to zoom inside a data center, so for instance, we were to look inside one of these data centers, so they don't exactly mention how many data centers they had at that time, but we know that there are at least multiple data centers. If you were to look inside the data center, the way that they've architected the system is such that if you were to see what they have is clusters. So they talk about these front-end clusters that have many web servers and many Memcache servers. So if you were to look inside a data center, they would have many clusters. Inside each cluster, they would have many web servers, many Memcache servers. So at one place, they talk about thousands of Memcache servers potentially in a cluster. And then they also have a storage cluster. And this is really the database, servers that are storing the data in persistent storage. So this is how within a data center, the architecture looks like. Many clusters within a cluster, many web servers and Memcache servers. And then you have a storage cluster, which includes the database server storing the data in persistent storage. Now let's look at how Facebook is using the Memcache server. So we looked at the architecture, and the architecture was such that after the load balancer routes the traffic to a web server, so we have the web server. The web server is going to be talking to a Memcache server. Let me call the Memcache server MC. And then we also have the database servers. So if a web server wants to make a GET request, so let's say it wants to read data corresponding to a key K, how does the web server interact with the MC servers, Memcache servers? So can anybody tell me what is the process? Yes, Eamon, please go ahead.
So first it will send the request to MC, and in case it didn't get data from there, then it will send request to database.
Okay, so Eamon is saying if there's a cache miss, go to DB. Okay, so let's say there's a cache miss, Eamon, and the web server then goes to the DB, read from DB. Then what will happen? That when GET requests are done, what happens is that the web server will send a GET request. And if there is a cache miss, that in that event, what will happen is that we'll send the update to the database server. And then the database server is going to, so then the web server is going to actually put the key onto the cache, update it onto the cache. So what I said was that it's going to delete it, which is not the case in GET, but that's the case in put command, as I've said. So, so that was my mistake. In GET request, once again, if there is a cache miss, the request is going to go to the DB, and then it's going to get updated it's going to update the Memcache server. And it is in the case of the put command that we are going to perform a delete operation. So again, if we were doing a read, and let's say this is the value, so what's going to happen is that we're going to fetch from the DB, and then we're going to update it in the Memcache server. And when it comes to the to write operations, what is going to happen is that we're going to first send the write request to the database, and then we're going to perform the delete request. Okay, so this is what was correctly said by Saf. So the comment that I made actually was with regards to the fact that when we are updating the database here, why did they not update the Memcache servers directly? And why did they invalidate the Memcache servers? So actually one thing that would speed up updating the Memcache entry would be to directly update the Memcache servers whenever there is a write performed. So you could imagine that an alternate design would have been that we first go to the database, and then we once the data is updated, the web server ends up updating the Memcache server. But this is not how it's happening. When the update is done to the database, the web server ends up deleting the entry. And only when a subsequent GET request for the key is made will we have the insertion being done at the Memcache server. And so this was one of the things that, to me at least, seemed did not appear to be a natural design choice, because it seems that this would incur more delay, because the next time a GET request will happen, what will happen is that there's going to be a cache miss. And then we are going to go again to the database server, read from the database server, and then update the cache servers. Why not update the cache servers right away? Okay, so this was one of the things that we will discuss why they're doing it this way. Okay, so in terms of the storage architecture, the first question I have is why all updates are being directed to the database. Wouldn't this make the latency of writes slow? So why is it okay for them that all the writes should go to the database? Why not just update the MC servers right away? So anyone, why are they updating the database directly? Faik, please go ahead.
To ensure consistency, they're just prioritizing consistency over delays right now, because if they update the cache and not the database, then there's a chance that future GET requests for the same thing will return a different result if the server queried isn't the one that has the cache change.
So excellent, Faik. That's absolutely right. As we said, they want the database to be the authoritative copy of the data. And so that's why they want to make sure that the database reflects the updated copy of the data. And as a result, they want updates to first happen at the database. And as you correctly said, if we were to update the MC servers first, then we may run into this issue that the database might have stale data, and some other GET request to another MC server may actually lead to stale data being read. Okay. But they were able to make this design choice because, again, they say that the workload is read heavy. So the number of write requests in proportion to the number of read requests are much smaller. And that's why they are ready to take the hit on slow writes. If the workload was such that they had a large number of writes, then this could have been a more significant performance issue, because then it would have meant that a large number of requests are going to the database and incurring the delay of reading from persistent storage. The other thing is that since they're saying that there is a master data center, and all writes are executed by that master data center first. This means that there is not only the delay in sending the writes to the database first, but there is also the delay of propagating those writes to the master data center, which makes writes quite slow because writes may experience this delay of going over the wide area network. Okay, so writes in their system can experience longer delays. One, because the writes are going to the database, and then because one of the data centers is the master, the writes are executed at that master data center first and then replicated at other databases, which means that the writes will have to go over the WAN. Okay, so updates are stored in the database first for persistence, for consistency, to make sure that it is the database which keeps the authoritative copy of the data. But as we said, it can be slow. And it's slow for two reasons. First, because the writes are going to go to the database, it's storing the data in persistent storage. And number two, writes will need to propagate to the master region or master data center. And that means that the writes are going to see the delay over the wide area network. Okay, so next, my question is that why do they invalidate the cache when they're updating the when they're making a write, when they're doing a write operation after doing the write at the database, the web server deletes the entry from the cache server? Why not directly update it in the cache server? Because that can save time in updating the Memcache. That doesn't seem to make sense as to why they are first deleting it and then waiting for a subsequent GET request. Eamon, please go ahead.
Delete is item content means that it will not create any incorrect value, result in incorrect value in the future. If we update, for example, initially it can be x is equal to 2, or let's just say if we update into x is equal to x plus 1, it is possible that some other have also updated to x plus is equal to x plus 1 into 3. And if you perform another update, it will be turned into 4. So it's much safe to delete and then to write because it is an item content operation.
So that's true, Eamon. And I also have a similar example that you mentioned just to illustrate why, if we were to update directly, what sort of consistency problems can we run into, right? So let me just walk through a similar example to the one that you mentioned. Okay, so again, just to remind you, we're talking about the process of updating a data item. And we said that the way that Facebook web servers are going to do it is that in the first step, they're going to update the database. And then in the second step, they're going to delete the corresponding entry from the Memcache, invalidate the cache entry. And the question was, why not update it at this step? And what Eamon has said is that this can lead to problems, specifically consistency problems. So let's look at an example in which there can be a consistency problem. So let's say we have this example where C1 refers to one client and it's making an update to a data item X. And in this case, we're just updating it to 1. And since all the updates go to the database, this update is first made at the database. Okay, so remember, you can think about this as C1 as a web server. And then let's say we have at the same time another web server making an update to the same data item X, updating it to 2 and making this update in the database. And then once this update is made, let's say what we have is C2 coming in and C2 then updating directly the Memcache server. So in this example, I'm assuming that instead of invalidating the cache server, what C1 and C2 are going to do is that they're going to just issue a put command directly. So the step one is going to be update the database. Step two is going to be just not delete, but instead of deleting, just update the data corresponding to the key directly in the Memcache. So it's going to issue a put command. So it's doing a put command and it's updating x22. And then what happens is that we have the second put command, and this could have happened because the web server C1 is slower than the web server C2. And now what's happening is that we have the Memcache server being updated with x is equal to 1. Whereas if we look at the DB has the updated value of x is equal to 2. So if we were to look at the DB view, it's saying x is equal to 2. And if we have the MC view, it's saying that x is equal to 1. So this is a case where we had a race condition because how the updates got reordered, leading to this state. Now, why this is problematic is that although Facebook is okay with tolerating stale data, and this is stale data, the problem is that MC server is going to keep responding to web servers, but that means that it's going to keep sending this value x is equal to 1 when a GET request is made corresponding to x until a subsequent update is made, which may be very long. And in this case, this means that the data can remain stale and users can we can keep showing users stale data unless a subsequent update is made, which can be long. And this is something that they want to avoid. They don't want to keep showing users stale data for a long time. But I will show you in the at the end of the class that something like this can still happen with the scheme that Facebook has adopted, which is delete. So we can run into race conditions with delete as well. And they mentioned this in the paper when they talk about stale set. A similar race condition can also arise and something that they had to deal with even in the scheme that they had where they would delete the directly delete the entry from the Memcache server. Okay. Yes, Fatma, please go ahead.
Sir, can't we deal with this by using leases?
Yes, that's the solution that they have for the scheme that they had, which is to use lease.
But if we do use leases, can't we just do updates?
Sorry, Fatma, please repeat.
If we're using leases, can't we just carry out updates then? Because in that case, put X1 will be, I think, invalidated and it will never occur.
Yes, that's true that if we use leases, then, but Fatma, can you just hold on, because since I've not talked about leases, I just want to hold on to this discussion so that when we talk about leases, I would like to first describe what a lease is, and then we can come back to this example and see how lease will solve this problem. Okay, and we can also talk about how the scheme that they had still suffers from this problem, and this is why it's not clear why using delete is significantly better. Okay, but just hold on to that thought so that when we talk about leases, then we come back to this. Okay, so we'll see later on that even in the scheme that they had, we can run into a race condition like this. And like Fatma said, there is a notion of leases that is used to fix this. And the natural question that Fatma is also asking is, why not use that concept to address this problem and use updates directly? Okay, the next question I had was that at a high level, they're getting this, huge performance of being able to process more than 1 billion requests per second. How are they able to achieve such high performance? So if we are to look at a MC server, the MC server may have a capacity of around processing a million or in the order of a million requests per second. Okay, and they are able to process a billion requests per second. So what are they doing in order to design a system that can handle billion requests per second? So how are they scaling their system such that they can handle such large number of requests? So what are some of the basic ideas that they're using? Anyone? Hamza Sajjad, please go ahead.
I think one thing that they used was utilizing. Am I audible?
Ji, Hamza, you're audible.
I think they utilize parallel requests and they structured all of the requests in different batches so that the network round trips were minimized and most number of items would be fetched for each individual request. So that was one way that they scaled to large number of requests.
Right. So what you're pointing to, Hamza, is that they do a large number of parallel requests, but for that, what do they need to do? They need to partition data, right? So they have huge amounts of data. So all these different key value pairs, so they need to have a way to partition that data. How are they partitioning data? Can anybody briefly tell me how they're partitioning data across servers? So how do they decide which key value pairs will go onto which servers? Yes, Fatma, please go ahead.
I think they use consistent hashing.
They use consistent hashing. So that's one idea that they're using. For partitioning, they're using consistent hashing. That's true. But let me ask you a follow-up question now. So it's true, like Fatma said, they're using consistent hashing for partitioning, just like Dynamo. But once they use consistent hashing for partitioning, there's a problem that they run into. And that problem is that when they partition using consistent hashing, they notice that some of the data is extremely popular. That is, some of the keys are extremely popular. We saw that in Dynamo as well, that what happens is that the load can be skewed across keys. So some keys might be experiencing a lot of GET requests, for instance, because these are popular data items belonging to, let's say, a popular page. And they say that some data items are extremely popular. And in fact, they mentioned this, that for some of the popular keys, they might be taking up 20% of the load on a MC server. So if you then map that key onto a server and other additional keys as well, you can likely overload that MC server. So how are they trying to solve this problem? Simple consistent hashing doesn't seem to solve the problem completely and can lead to overload. Ashir.
Sir, I think they're using different pools for different kinds of data. So I think they've got an app pool and a regional pool. And in the regional pool, they have data that is large but is requested infrequently. And in the app pool, they've got data that is small but is requested very frequently. It is something like that.
So Ashir, how does that completely solve the problem? Having different pools, how does that completely solve the problem? Here, the problem is that if you're just using consistent hashing, you may end up mapping, let's say, multiple popular keys to the same MC server and then overloading that MC server. Overloading the MC server would mean that the MC server the requests are going to see longer delays because of queuing, and that in turn impacts their goal of low latency. The question is, how are they solving this problem? Having different pools just means that we are just sort of dividing data sets into different pools. But how does this handle this specific problem of popular keys? Fatma.
So basically, say our different pools can be such that we can have a pool which which has keys which are frequently accessed, but they're expensive to access through the database. And we can also have a pool which has keys which are frequently accessed, but they are not that expensive to access from the database. So we choose to keep those keys which are expensive to access through the database and frequently accessed inside our meme cache. Other than that, we can also perform data replication on the front end on the different routers, and that means that the load is divided amongst several servers instead of just on one.
Excellent, Fatma. So this, the second point that you've mentioned is something which is fundamental in how they resolve and try to address this problem, which is replication. Remember, we have discussed replication primarily to provide more fault tolerance. We keep copies of data so that if one of the server goes down, we have replicas. But here they're using replication to improve performance. And the way that they're using replication to improve performance is that if you have popular keys, keys that are fetched regularly by a large number of web servers, then if you have replicas of that key, that means that you can divide the load on different servers for that same key. So replication can actually help you improve your performance. And so to address the problem of popular keys, you can think about replicating those keys onto different servers so that then the web server load is divided on these different servers. Okay. So replication is the key idea that they're using. And more specifically, if you have very popular keys that are experiencing very high load, that is a large number of requests are about getting those keys or updating those keys, then replicate them on different servers and divide the request between those servers so that you can reduce the load corresponding to that key. Okay, so replication is the key idea that they're employing to address this problem. Now, the consequence of doing partitioning, which is how they first scale to a large number of, how they scale their system to handle a large number of requests. The problem is that this leads to a communication pattern which they call all-to-all communication. And the problem they mention is that what can happen is that you have web servers which are then contacting many different MC servers. So each web server can end up contacting every MC server. And this can lead to this communication pattern where a web server is contacting all MC servers. What kind of problems can this lead to? Why was this an issue that they had to really tackle, because this was leading to performance issues? What kind of performance issues they mentioned related to all-to-all communication? Can anybody describe some of the problems? Yes, Saf, please go ahead.
So there is a large communication overhead attached in this scheme, because if each node has to communicate with all other nodes, then this means that there will be a lot of messages in the network at a single point in time. And if this is a network bottleneck, then that could lead to severe latency issues.
So if the network is bottlenecked, can we get a little more specific? Why do you think the network will become a bottleneck here? Is there a specific issue that they mention why the network can become a bottleneck with such a communication pattern? Fike.
One server can become a bottleneck if it's having a really popular key, because a lot of the bandwidth has to go through it, and it's just one server that has to process everything, so it's slowing down the entire system.
Okay, but then it's the server becoming a bottleneck. So Fike is saying that a web server can become a bottleneck because then it's processing a large number of requests, sending a large number of requests to MC servers. Is this the key issue that they faced when it came to all communication? Fatma.
Sir, so I think the Memcache becomes a bottleneck, not the web server. And the reason for that is when, as Spike mentioned, that when Memcache is servicing a very popular key, then it receives a lot of requests from different web servers, and it has to reply to a lot of different web servers. So sending those replies can act as a bottleneck. Some might have to wait longer, um, and that might hinder the rest of the processes.
Okay. Again, are there any other issues that they mentioned regarding all-to-all communication? So we're talking about MC servers becoming a potential bottleneck, but for that we've said they use replication to divide the load. But is there something inherent in all-to-all communication that can create performance issues? So anybody else would like to share any issues that the paper mentions? So the paper talked about in-cast congestion. So can anybody tell me what that is? They said that all-to-all communication can lead to the problem of in-cast congestion. And this was a serious problem for which they had to then take action. How they ended up designing different clusters, had to deal with this problem. This was one of the major problems they had to deal with. So anybody on what that in-cast problem might be? Okay, so they talk about this problem of in-cast congestion in the network. And this problem is that the web servers and Memcache servers are connected by a network. And this network has to have switches and routers. And what they mention is that when you have a web server sending requests to many MC servers, what they observed was that these MC servers may respond at the same time or in very close proximity in terms of time. And what they observed was could happen is that the switches or routers may receive a lot of responses from the MC servers at the same time, and the buffers of switches may end up overflowing because of congestion. And that leads to packet losses, and which in turn means that there's going to be more delay because you will have to resend the traffic if you're using TCP, or otherwise you will not be able to get responses because the message is lost. So in-cast congestion is when you have a communication pattern where you're talking to a large number of other servers, and those servers can reply back at the same time. And those responses then, when they come at the router that's going to be sending the traffic to the web server, that router's buffers can fill up. And when the buffer capacity is full, any other packet, any other message that comes in is going to be dropped. And that can lead to performance issues because that means the message is lost. In the case of TCP, you'll have to retransmit the message. In case of UDP, that's going to be a lost message. So this is the in-cast problem that they talk about. And this is a consequence of all-to-all communication pattern. And what this problem does is that as you increase the MC servers that a web server can talk to, this problem can get worsened because then you might have a large number of MC servers sending responses at the same time and the switch or routers buffer overflowing. So this is one of the problems that they mentioned, and they said that as a result, they ended up dividing the set of MC servers and web servers into clusters. So it's not like they have a huge cluster where a web server can talk to all the MC servers in that cluster. Generally, what they have is they divide the web servers and MC servers into clusters, and most of the communication is happening within that cluster. And the reason is that you can run into the problem of in-cast congestion, which can then cause significant delays. Another problem that they mention is of the fact that if they're using TCP, and they use TCP, if you have read the paper, when it comes to doing put requests, when they're writing data, they use TCP. And they say that when they had to maintain TCP connection between every web server and every MC server, the overhead could be significant because the amount of state that you need to keep for each TCP connection could be significant. So as you know, TCP is a stateful protocol, connection-oriented protocol. So there is state that TCP keeps, also about unacknowledged packets. And so they said that because they have within a cluster, even within a cluster, thousands of servers, if they allow this pattern where a web server is talking to all the MC servers, then you have a large number of TCP connections that you need to keep, and the state corresponding to that TCP connection can be huge. And that was something that was a problem that they observed. And so they also wanted to keep that to a manageable proportion. So these were the two key issues that they mentioned when it came to all-to-all communication. One is incast congestion, and the other is the fact that you need to have lots of TCP connections. And each TCP connection, for each TCP connection, you need to store state. And when you have a large number of MC servers, then that means that the number of TCP connections increase and the amount of state that you need to store increases. Okay. How do they scale the Memcache servers? You know, as I said, this is one of the reasons why they have multiple clusters per region, and why they did not add more and more MC servers to a single cluster, because they want to avoid the problem of incast congestion, or mitigate the problem of incast congestion. And then the second problem is they want to keep the number of TCP connections to a manageable number. Do they replicate all objects? Can anybody tell me? We know that they replicate in the MC servers popular keys, but do they replicate other objects? So can anybody tell me whether other objects are replicated or not? Fatma, please go ahead.
Answer, not all of them are, because if a key is not that popular and will only be accessed once or twice, there's no need to replicate it, I think.
And that's true. And the reason why you don't want to replicate such keys is that RAM is expensive. And replication means that you end up using more RAM. Remember, the Memcache servers are storing all the data in RAM. And so if they replicate, they need more MC servers. And if the keys are not popular, then they didn't see any real utility in replicating them and ending up using more RAM. So here I want to just summarize the benefits and the potential disadvantages when we're using these two basic ideas, partition and replicate. So this is something that we've seen. In order to scale a large service, we have to partition the data across that service. And in order to provide fault tolerance, we need to replicate. And so this is a list of the benefits and potential disadvantages of partition and replication. Let me just stop here because I just noticed, sorry, that I have gone over time because we have a quiz today. So I'm going to stop here, and then we're going to come back in the next class and resume our discussion because there's still a lot of points to discuss about Memcache service. So we're going to stop here. You can get started with your quiz. All the very best.